All right, so welcome back to the second application of interest. As promised, I will be telling you a little more about the exam scheduling problem, which is actually a pretty relatable problem. So let's say that we are in a university setting where there are n classes and all of them need to have an exam scheduled during, say, exam week. And these classes are going to be scheduled in one of our available rooms during one of the different available time slots. So these are the three things that we want to watch out for, right? And we are going to assume that every exam will be held in one room and one time slot. So we are not going to require people to split into multiple rooms to be accommodated. Every room has sort of a size and every class has a strength. So it's only you can only schedule the exam for a particular course in a particular room if the capacity of the room fits the strength of the class. Otherwise, we're basically not allowed to split a class into two rooms. And similarly, we get exactly one time slot. We don't have any of these courses trying to do multiple exams or no exams. Every class, for simplicity, we assume will have exactly one exam. Now, another element that we need to keep in mind is invigilation. So we have P invigilators who are willing to basically proctor these exams, but we have a limit of only 5 exams per invigilator. So 5 exams per person here, and each invigilator also has a certain set of times when they're available. So we have to keep in mind their time slot constraints as well. So every invigilator is going to tell us which time slots work for them and which don't. And we have to make sure that we give these invigilators times that they're available, and we never give them more than one exam in overlapping time slots. They cannot be at 2 places at the same time. Okay, so these are essentially the constraints. Let me actually put in the input a little more explicitly so that it's clearer. All right, so this is what we have coming in as data into the problem. So the E array basically tells us about the strengths of the individual classes. So it's the enrollment numbers, if you like. The S array tells us about the sizes of the rooms. So S of I tells us how many people room number I can accommodate or handle. And the A array here is sort of an availability array for the invigilators. So what this tells us is, given a time slot which is between 1 and t, and given an invigilator index which is 1 and between 1 and p, the Aij entry is true if the invigilator indexed j is available at the ith time slot, and it's false otherwise. So that's just a Boolean 2D array giving us information about the availabilities of the different invigilators. Now that's going to be the input via the E, S and A arrays. That sort of captures most of the constraints that we talked about, and there's this one additional constraint that we just put down here explicitly, which says that every invigilator can only be called upon to invigilate at most 5 exams. We don't want to overburden anyone. So that's the input. And what do we want as output? We want a valid exam schedule. And of course, we want this provided it exists. And we can basically report no otherwise. If it doesn't exist, then we can say, well, this is not a feasible set of constraints. You have to loosen something up, either bring in more rooms or bring in more invigilators or request them to be available more or allow them to invigilate more than 5 exams. You have to do something to make it happen. But if it's feasible, then we want to be able to figure out a valid schedule. Now, you can think of these classes, rooms, time slots as resources, just as we talked about in the tuple selection problem. And let me actually put up a flow network for your consideration here based on essentially the same idea that we had when we were talking about tuple selection. So I'm going to have here a vertex representing every class. So that's going to be n vertices in this box. And now classes are most naturally constrained with rooms. So let me put down rooms next. Well, I've thought through this in advance. When you are solving a problem like this, you might have to experiment with a few different layouts and combinations before you hit one that perfectly makes sense and matches up with the specification that you had in mind. So after rooms, I'm going to have a dibba here for time slots. So here we have one vertex representing each conceivable time slot in the picture. And then finally, I'm going to represent the invigilators at the end. So that's going to be P vertices here, one for each invigilator. And just as we have been doing for the matching problem, the tuple selection problem, and so on, I'm going to add a source here, which is going to be adjacent to every class vertex. And we're going to have a target, which is going to be adjacent from every vertex that represents an invigilator. So this is T. And now we need to set up the intermediate edges. Well, let's come in from right to left this time. So between the time slots and the invigilators, we throw in edges based on the A array. So we're going to say that we have an edge going from a time slot here to an invigilator here, exactly when that invigilator is actually available at that time slot. If they're not available, then we don't add this edge. Okay, so these edges are driven by the A array, and we'll come back to this, but we will see that it's enough for them to have a capacity constraint of 1. Okay, now between the rooms and the times, there is no real constraint that says that, well, it's not auspicious to have an exam in this room at this time, so we just throw in all possible edges here. What we do want to be careful about is to make sure that a room is not overbooked, which is just to say that we don't have a situation where, we've scheduled more than one exam in the same room at the same time, but that is something that we will be able to achieve using just the capacity constraint. So for now, the edges allow us the flexibility to use any room at any time, which is, as we will see, the appropriate thing to do. Now coming further up, let's talk about the relationship between classes and rooms. What do you think the edges should be here? Well, we have this data about the enrollments and the class sizes. So it's natural that we want a class to be adjacent to a room only when the room can actually accommodate this class. So let's say this is class I and room J. So we want that edge to be present only if the strength of the class I is at most the size of the room J, right? So you throw in all of those edges here between the classes and the rooms. We don't want to be able to assign classes to rooms that can't accommodate them, right? So that's essentially the construction of the network. Now let's go over the capacity constraints, and let me just shift this diagram a little bit to the left so it feels a little more centered. Right, so how do we want the capacities to be worked out? Well, this time let's go from left to right. So from the source to classes, we basically want every class to be scheduled, and that's going to be reflected, as we can anticipate, in the path flows that we are going to eventually get. So the capacities that we associate with the edges from emanating from S is all 1. Okay, so we want 1 unit of flow going into each class, and now we're going to chase those flows down in the flow decomposition eventually to actually pull out a schedule from the final max flow that we get. Okay, between the classes and the rooms, we don't particularly care. We have 1 unit of flow coming in, and this unit of flow, remember, we are, without loss of generality, we are talking integral flows here. So this 1 unit of flow that comes out, that comes into a class will have to get out into one of these rooms, and so we don't really need an explicit capacity constraint out here, so we'll just leave that alone with some large number. But on the other hand, it is important to impose a capacity constraint further down here between the rooms and the time slots. The effect that this capacity constraint will have, and I'm proposing a capacity constraint of 1 here, is basically to say that, well, once a room, notice, will have like an incoming flow from multiple classes potentially. And so there are all these classes who want to get scheduled in this room because, well, it's going to be one of the rooms that can accommodate this class. And now let's say that there are 5 classes that want to be scheduled in a particular room. Now that room has to identify 5 time slots which are all distinct, so that it can actually accommodate these 5 requests that are coming in the form of flow. So basically we want this flow to be split across 5 different edges. We don't want that, for example, 2 classes go into the same time slot from a given room. That would basically result in a clash. So a capacity of 1 will basically force this incoming flow to in fact split and go into different time slots, and then will be good in terms of clashes. And similarly, because we don't want invigilators also to be doing double duty at the same time, these are not Zoom exams, so we're going to have a capacity of 1 here as well. And it's the same idea. You have a lot of incoming flow into one time slot. So this is, let's say there's an incoming flow of 7 into some specific time slot. That just means that there are 7 exams that have been arranged at a particular time in 7 different rooms if the flow so far is feasible and valid. So that 7 units of flow needs to go out and reach 7 different invigilators, because we don't want a situation where one invigilator is trying to do multiple exams in the same time slot. And finally, we have the edges going out of the invigilators into T, and this is the burden capacity constraint. So here we have a capacity of 5 on all of these edges. This will essentially ensure that no invigilator is doing more than 5 exams, so nobody is overburdened. That's what this capacity constraint is going to ensure. Now it's a matter of checking in a fairly straightforward manner that if you have a flow that has value n, that must mean that it saturates all of these edges coming out of the source. Then you can actually trace that flow all the way to T, and you can decompose it into these n different paths, and each pathway basically gives you a schedule for that class. So you can try to follow the flow, so to speak, getting out of S and then pursuing the path flow corresponding to it. So that's going to hit a room, it's going to hit a time slot, it's going to hit an invigilator before reaching T, and all of those will basically give you a schedule for that particular class. And you can repeat this for each class to recover a schedule. And the fact that the schedule respects all the constraints we have in mind for the original problem is going to fall out of the way the capacity constraints have been designed in this network. And that's just a matter of straightforward validation. And just to establish equivalence, you can also show that if somebody gives you a valid schedule, that can also be realized as a saturating flow of value. I say saturating flow simply to mean that all the edges out of S are in fact saturated. So if somebody gives you a valid schedule respecting all constraints that schedules an exam for every single class, then that actually can be realized as a max flow in this network. So notice that, well, you already have a cut right here with the set S being just the vertex S. This is already a cut whose capacity is N. So you know that you cannot do better than N. So if you have a valid schedule, that's in fact also going to correspond to a maximum flow out here, right? Again, by valid schedule, I simply mean a schedule that accommodates all of the classes, all of the exams that we demand, and does it in a manner that respects all the associated constraints that we have been listing out. So that brings us to the end of our discussion around exam scheduling. I'm going to leave the details of validating that the equivalence goes through to you, because I do hope that at this point it's fairly transparent as to what's going on. It's just a matter of putting all the definitions together. But the main thing that I hope you took away from this is the idea of how you think about building a flow network that can capture the essence of your problem. How do the connections get set up? What capacity should we come up with? These are questions that you want to be asking yourself whenever you decide to solve a problem by reducing it to network flow. And the best way to really get the hang of this is to just practice a lot of problems. So we will be doing that through the assignments, of course, and the notes will have pointers to some additional practice problems. And if we have a chance, we'll be going over them in the live sessions as well. So do make sure to get plenty of practice to go through this process of designing a flow network, capturing the problem multiple times to really get a feel for how this is generally done. We're going to see one more example, and I think it's a really fun one about who is going to win an IPL tournament. Basically, the question is if it's even feasible for your favorite team to win. So I'll tell you more about that when we meet next.